Good morning, everyone. Uh, Thanks for joining us for day 4 of the Scientific Machine Learning Summer School. As we have learned a lot over the past 3 days. But today we have guest speakers who will be talking about the research, and hopefully we can learn a lot from them. So we're already 5 minutes late, just waiting for other students to trickle in. But let's get started with our first speaker, Dr. Lifen Wang. He's a professor in Department of Physics and Astronomy at Texas A&M University. His research interests include astronomical instrumentation, dark energy, dark matter, near-field cosmology, etc. He's also doing research on machine learning-enabled studies of large astronomical data sets. And today he's going to talk about AI in astronomy and astrophysics. So, thank you.
Hey, good morning. I looked through the program that you guys have gone through the theory, and in the past 3 days, I think you have learned, for the students, you have learned some of the basics of the theory and applications of AI. And today, I'm just going to show you some examples how AI is being applied in astronomy. So basically, AI, like in every other field that that are still actively progressing, AI affected deeply in all those research disciplines, and really in astronomy is transforming how we explore the universe. So why AI is important in astronomy, in modern astronomy? So many years ago, when I was a postdoc at Berkeley, there was a talk given by somebody, a very well-known, famous astronomer, who talked about their observations of a number of active galactic nuclei, which basically there is a black hole at the center of every galaxy, and the people are very interested in understanding how black hole, the physics related to black holes. And at that time, the person gave the talk, showing the spectra one by one, just how those spectra are different from one and the other. And then in the audience, there were a lot of physicists. The talk was given to a broader audience, including astronomers and physicists. And one of the physicists with a Nobel Prize, the Norin, he asked the question, so why didn't you observe all the galaxies in the universe? That was like, at that time, people immediately burst into laugh. It was impossible to think that we can ever observe more than maybe 1,000 AGNs in great spectroscopic coverage. But today that has changed. Today we are really mapping the whole sky for just trying to observe every possible galaxies in the universe to get information, one way or the other, to probe, how they look like, to find, anomalies, and to identify physical processes that are interesting. So in the upcoming decade, actually in this decade, some of these telescopes will, in the upcoming years, astronomers are going to be provided with the opportunity to use some of the unimaginable telescopes, just a few years ago. This includes, one like you already know about, that is the James Webb Space Telescope. Okay, the James Webb Space Telescope has, is actually the most expensive scientific experiments or laboratory ever built in human history. Okay, it is 10 times or a few times more expensive than the Hubble Space Telescope. It is more expensive than the Large Hadron Collider in Geneva. Okay, so that telescope is already being launched and is doing a lot of collecting a huge amount of data uh, and making breakthrough discoveries every day. And then there is the Large Synoptic Survey Telescope, or LSST, which is going to be built in Chile. It's going to be complete or in operation just in a matter of a couple of years. And that has a gigantic camera, that is many 10 times the field it can cover is many times larger, well, many times of that of the moon. So basically, you can imagine the moon as a reference. But now you take a very deep picture of that, you know, 10 times or 100 times of the moon size and all the way through the entire universe, more or less. Okay, you collect data on all the galaxies and the stars in that direction. And LSST plans to actually, observe that, taking multi-epoch observations of that deep sky, of the whole sky, of the 4 pi sky. So you can now imagine how large the volume of the data is going to be. This basically is really a perfect playground for all the AI techniques that you can imagine. You want to classify the objects, whether it's a star or it's a galaxy. If it's a star, whether it's a star of this type or another type, whether the star has planets, okay, whether the planet can harbor habitable planets, which is of great interest in astronomy. And then there is also another space telescope, the Rubin Observatory. That's going to be launched also in a few years if the budget is not going to be cut. There is the NASA's budget cut is primarily, a major, well, we'll cut the program away because this is another very expensive telescope going to be built, and it's going to be launched into space and do this whole sky deep surveys to search again for alien planets, to do cosmology study, to study how the universe expands. So it's all going to collect a huge amount of data. And AI is needed for all these projects. And actually, AI programs have been built, for all these observatories, that, well, from almost every aspect of the operation, from the operation of the telescope, actually how you run the telescope, how you control the telescope. Those are actually also, part of this AI, part of the aspect that AI can contribute. And the operation of the telescope, collection of the data, and the processing of the data, and the discovery, and then from discovery to science to physics. Okay, you can see, every part of this involves a huge amount of data. Okay, that's why, there are statisticians interested in astronomical data. There are, the people in, different field when they develop new things, always, they can find applications in astronomy. Okay, so I gave you a few more detailed examples here. So for instance, this is a simulation of the planet discovery that can be achieved. One of the scientific target that AI may contribute, this is the search for alien planets. So you can see how, tricky this is, or the technical challenge here. You have, this alien, these planets are very dim. It's very hard actually to detect them. It's almost impossible to see the light directly from a very far away star. But there are just chance alignment of stars in the sky that makes this possible. So this is basically using this. If you have this shows if you have one star just moving in the front side of a background star, just moving. This is just the movie. This movie plays just repeatedly, but it just basically as they you observe these two stars. You cannot resolve their motion, actually. They move very slowly. But stars are very small. So when they move, you can see their brightness will change. When they move, the brightness change because a effect that was discovered by Einstein, that was proposed actually by Einstein, is that the presence of matter will distort the space. The geometry of the space along a certain direction, the direction from us to the star. So when that distortion will create an effect that effect is like a lensing, a lens, because of the made of astronomical object, because the star will bend the space-time, light will go in curves, not in straight lines. And that's effective like lens. So you can see the brightness of this star in the background is being magnified as another star goes in front of the other one. And this magnification can be sometime a few times, like a factor of 2 or 3 or even larger. And it has the perfectly symmetric structure. So how the way it goes up will also be the way it goes down. But this is assuming stars are spherical object. And the effect of the planet can be detected through a narrow spike here. Just when the planet goes in front of the star, the other star. So all you want to, you have to, to find this kind of events. This is one out of like 10 million stars that will do this. But the universe is full of stars. So you will always be able to find this, although it is very, very difficult, okay, because it's very rare events. But you have abundance of those. So you're going to find a lot of this kind of, some stars. The stars are always blended with some background stars. Here it is exaggerated and a single star, but it's always blended with a lot of billions of stars. Okay, tens of hundreds of billions of stars. So the challenge is first you had to identify something like this. You had to discover this, and you have to discover this early. Okay, you had it. Then you can, hopefully that somehow you find that a star is brightening or doing something funny. That's like it's being magnified by another star, by a foreground star. Then you need to coordinate your observations somehow to, take data during the time when the planet goes across that. Okay, you cannot miss that. If you miss that, you're not going to see the planet, because planet, this spike lasts only for like a few days. And for Earth-like planet, which is the goal, we are trying to find the Earth 2.0. Okay, 2. This another version of the Earth. When you try to do that, you can see this thing. That only lasts for half an hour or something, a few 10 minutes or something. So if you miss that, then your effort is in vain. Okay, so you can see now the challenge is, you need to somehow schedule your telescope once you discover this, and then you have to be able to schedule your telescope to take enough data during that half-hour time window, and then you will be able to probe, to say something about this planet. Okay, and of course, the other telescopes like James Webb Space Telescope, they can always, once you discover something, you want other telescope also to, want to trigger observations of a whole network of telescope who are able to take data to observe this. You can say this is another challenge, to coordinate observations and also to discover the candidates, to coordinate observations, and then get into the stage of what data are taken and analyze those data. And we are interested in detecting water or ice or any signs of life on this planet. Okay, another example, this is the so-called Astro PT. Okay, this is just like a chat GPT or something. Astro PT is a kind of neural network based, transformer based algorithm that trying to study the world of galaxies. Okay, there are like about 100 billion galaxies in the universe. And as I said, we are going to take images of all these galaxies in the universe. So this Astro PT is trying to study the galaxies in a large language model or build foundation models with those images. So effectively, in this particular application, people can come up with smarter ways of doing this for sure. So this way, basically it built these tokens, which is like the word in language. They built the tokens by breaking, this the whole galaxy into smaller pieces. So here they use a 16 by 16 pixel patch. Okay, like each of that patch you can assign, and you say that's a word or something. Okay, in a large language model, and you somehow then organize that patch in certain ways. Okay, that's like a sentence or something. Okay, so you say here it organizes it as a counterclockwise kind of thing. Okay, so you can say once you do this, then basically you build each galaxy is like a sentence somehow. Now you can try to train your neural network. It's a rather straightforward thing to do. And you basically can borrow whatever tools you can, that are available. And this can actually now, because it's a foundation model, it can integrate many, many things into this. You can have this, and you can also have the, if you have spectroscopic data of this galaxy, or you have these galaxies in different wavelengths, different colors, you can lump all of those things in your model. So basically, in the end, you will be able to study these galaxies. Really, whatever data you can put them into your model, and this will give you some kind of analysis based on large language models. Okay, and you can see that when you do this, you basically have the whole universe, all the galaxies somewhat studied. And some galaxy, there was a report, for example, I don't know if you heard about that. There was a report a few weeks ago or months ago about the universe being rotating in one way, not favoring the rotation in one way, not the other way, like a right-handed or left-handed or some kind of rotation. You can say, that's like talking the language in the forward way or backward way. Okay, you can sort of identify how the spirals go, in a if you can through this kind of algorithm. Okay. And all these are available. If you want to play with this, you can just go to the site and play with this. But these are very primitive. These are by far not done yet. These people actually publish something very, very crude because there are a lot of issues with this. It's just not all galaxies look like this. Not all the galaxies are you can do this 16 by 16 pixel breakdown. Okay. But this is something I think that will eventually be very interesting. So Another thing in astronomy is to find something that is changing in the universe. The universe is actually live. The universe is very active, and it's making supernova. Stars live and die, and when they die, they becomes very, very bright. And the universe is also uh, full of wonders, such as sometime it may produce this very strongly distorted arcs because the space-time is distorted by massive clusters of galaxies or galaxies. You can say, this is actually showing an example, of a how a galaxy which should be normal, actually a normal galaxy that's being its image being distorted in space. Okay, how these images are distorted, what is involved there? What is actually what it is the matter that is responsible for this distortion? Okay, whether it's there is a mistake in Einstein's theory of gravity, something like that. And sometimes you may even find some supernova explosions on this distorted image or elsewhere. Supernova is just so abundant. There are like 10 supernova exploding in the universe every second. So you can see there are a lot of supernova in our universe, but finding them is very hard because each galaxy has about 100,000 billion stars, and only one is exploding in every 100 years. Okay, you can say it's just in terms of total number is huge, but in terms of the the fraction of the stars we observe versus the supernova versus the fraction of the stars we observe is a tiny number. How can we discover them? So astronomers develop the tools like subtracting images of different time and then see what's left. So here, for example, you subtract these two images taken at different time, and now you then try to compare and then see you know whether there is some residues. So this you can see from huge number of stars, then you get, oh, there is something brightening. Some stars got brighter. That could be a supernova, but finding them requires this dealing with large data. So here are some examples of this, just to show you. Actually, there is well, maybe you can see, there is actually well, maybe this one is better. So you can see, there's a little blob here which is not there, and this, could be a supernova. And here the subtraction of the image in different time. You can see how the supernova actually evolve with in brightness. Okay, and also the artifacts of the mis-subtractions, because your subtraction can always be wrong. So, and you produce a huge amount of fake signal. When you go through this process, you find a lot of fake alert. Maybe well, a million to one, or a few, at least 10,000 to one. Most of the candidates you're going to find are fake. So how can you remove those? What we are doing is through AI trained models. AI can do that. In the beginning, of the research, we use human eyes. We get a lot of undergraduate or graduate students to screen them one by one with their naked eyes. But later on, as AI technique becomes available, we are also smarter because of that. So AI can actually do all those things for us. So we can tell whether a candidate is real or not based on AI trained models. So here is another example to show the problem we usually face. This is a typical point spread function for people doing imaging processing. This is just, if you have a telescope of infinite resolution, you're going to see a point source, a different star like this. but you're not going to be able to see that because some technical issues, and also it's always unstable, the instrument. So there are always small changes there, but a little small change will create a fake signal in your image. Okay, so you need to be sure you are able to handle this. And how can you do that? The way to do that is actually through some AI algorithms. So here I give you some examples of how ugly this is. You can see, when you try to do this kind of subtraction, this is the original image. I didn't show, you subtract this image, taken of this galaxy's, image taken at different time. You get with different algorithms. We played with this. You can see, in the end, you get something really, really ugly. And there could be one thing like this that is real. And some of these are obviously unreal, but how do you know? You need AI to tell that. And another example, is about the search for extraterrestrial intelligence. The SETI program. Many of you have heard about the Breakthrough Listen program. That that is, that program uses radio telescopes worldwide. Basically, every telescope they can get their hand on, and also they are building big telescope arrays. Those are radio telescope arrays. So, this is uh, so their goal is to just keep listening, always listening. It's like turn your radio on. It's really not different from turning your car radio or something on, and keep listening and recording. And recording and listening every second, every fraction of a second actually. So they record huge amount of data. Okay. And then they do their analysis and say, oh, if any of those noise or whatever signal they hear from those radio telescopes, if any of the signal match a pattern that is from extraterrestrial, region and space, and then say if any of this can match into some kind of expected tech technique what is this called, techno signatures. Okay, something like a technology, like unnatural things from extragalactic object. So how you define those techno signatures? Well, that you more or less you generate some kind of stimulated signals, or you learn from our own signal, like our own cell phone or whatever signals, and then then you try to see if you can identify any of those from extragalactic sources. But you can see this is very hard because that means we are the signal is buried underneath this all the techno signatures of our own. Okay, and you collect a huge amount of data. Now you try to find something really, really faint, weak, and so the technical challenge, you can say, it's almost the same as it experienced a its progress experienced the same kind of experience that we had with supernova or the cosmic transient search. That in the beginning, people do this with the humans. So humans, they program actually the Berkeley group actually made a program that can run on a screensaver on every computer. I don't know. Some of you may know this. Actually, I invited that person. I was, the person who made this. I know him pretty well. So he made a program that can run on everybody's laptop or screensaver. At that time, you just have a computer, you leave it idle or something. But if you are willing to contribute, your screensaver will run the data processing for the SETI program project, And then you can, if you find anything, humans will try to identify what is interesting or not. Yeah. But now that's also being replaced by AI. Basically, the whole thing, we don't need human interaction. Well, intervention or interaction to really to tell whether, this is a target, for instance. This image could be something technological, not random. Okay. And then there could be, if you find the feature signatures like this from the extraterrestrial object, you may say, oh, there could be something, aliens trying to communicate and sending us signals like that. Okay. So you would think this is so difficult, maybe it's impossible, this is just not realistic, not even science. Okay, but let me tell you, in a few years, astronomers are going to build a telescope that is called SKA, Square Kilometer Array. That will be able actually to detect radio signals from some extraterrestrial object that is like the nearest star. The radio tower of an just typical airport located on that star. Okay, just that kind of signal will be, our telescopes will be sensitive enough to detect that kind of communication signal. Okay. So all this, will imply huge progresses in science and in our understandings of the universe. Okay, so AI can also be used in gravitational wave detection. This just got a Nobel Prize a few years ago. Cosmology, this is just concerns with how our universe expands out of what will happen to our universe eventually, and what is there in our universe. Okay, this is cosmology. And as I said, telescope automation, observing, planning, all those things. Those are going to be affected by by AI. Okay, I'm now just zooming into just go very quickly on the on a few examples that I did with my former students. I'll say, well, a lot of work actually done by Gisa. Um, so let me say very quickly how AI can deal, as an example, AI can deal with very complicated systems, both observationally and theoretically, and learn, from both. Okay. And well, you can see AI was actually built for, ideally for that. You have very complicated data set. You have very complicated physics of high dimensions. And then you somehow reduce that dimension to find out to draw a figure that the human brains can understand. Okay, so that's the goal for these studies as well. So what is a supernova? So a supernova is the death of a star. So basically here there are many ways the star can die. So here we're going to focus on one particular kind of star that dies as a white dwarf. A white dwarf is when a star exhausted all its the hydrogen and its core, it turns into a carbon oxygen bare core object. It's made of purely carbon and oxygen, but carbon can further be burned into iron, all the way to iron. When that happens, it's like a thermonuclear bomb. And a thermonuclear bomb explodes and can become very, very bright. It can overshine all the stars combined in a galaxy. So makes it so bright and it becomes cosmologically interesting because we will be able to observe them to very large distances. In fact, with today's telescope, such as JWST, we are able to observe type 1a supernova all the way through the entire universe. What do we mean by the entire universe? So our universe is actually limited. It doesn't go to infinity. So it actually goes to a distance. Then beyond that, there would be nothing. There would be no galaxies. Okay. So this supernova, the data we can visualize it like this. So on this horizontal axis, we have the wavelength. So it's going to radiate a kind of spectrum that is wavelength dependent. And then on the vertical axis, it's just the time evolution. Yeah, well, this is -15. This is early time. Yeah, this is just immediately after the explosion, and the light becomes brighter and brighter. Overall, and then it falls off and it becomes dimmer. But its spectrum, in the beginning, it is brighter in certain regions and dimmer in other regions, and that time evolves. So basically, what the data we are collecting, the ideal case data we are collecting is like this. Okay, it's like a two-dimensional manifold that is, a function of wavelengths and the time. Okay, but we will never be able to get this kind of data because we cannot possibly follow a supernova with this complete coverage. So we just take samples, of this, a little bit spots, something. But we try to rebuild this manifold. Okay, because we want to understand everything about the supernova, we need this manifold. But we don't even, we are nowhere close to being able to get everything there. So what we get is a time evolution of the brightness in different color, in different broadband. We don't get the spectral features, in this kind of light curve evolution. And also, well, we want to rebuild the whole thing. That's the goal. You can say, this is, basically what the first example we want to deal with is just empirically rebuild the manifold. And the other thing is the physics involved. The physics involved is really difficult to solve because the explosion itself, a nuclear bomb, can you simulate the explosion of a nuclear bomb? Yes, today we can actually. In the laboratory, on computers, this can be done. And it's very complicated. In astronomy, yes, that's also the case. And the explosions are three-dimensional at least. Three-dimensional in terms of the geometry, but also it's actually at least six-dimensional in the phase space if you get velocities involved. Okay, it's actually seven-dimensional if you get the time involved. So, and if you get the chemical structures, all those things involved, it can easily go to a dimension of 1,000,000 if you want to count on that. Okay, you can see how difficult the problem is. This is a problem with huge dimensions. Okay, and now you want to model this thing and try to build a model that will basically match whatever you can observe. You can see both ways are so complicated and of very high dimension. Okay, your observations are always limited because you cannot really observe all those dimensions. For one supernova, we can only observe through one direction. So it's all our information. There are a lot of things that are missing. Okay, so we can only observe in one direction, and how can we extrapolate from this very tiny amount of observation to now try to learn the assembly of a event? So this is actually a mathematical challenge. It's like really we don't have everything, but now we can observe something we think similar by a large number, like 1,000 of these observations, but they are all different. So now, but they share something in common. We want to learn from what they share and then try to identify their individuality. Okay, it is like this. Basically the informations are broken somewhere. We don't really get the chain of the whole chain of everything being connected. So here, to do this, but AI now basically is trying, we can somehow, based on what we have, the data we have, and then, maybe for this signal it's broken here, for another signal it's broken somewhere else. And then we try to, when we lump all things together, we study the assembly, the whole sample of the signal, try to rebuild this. So this is basically our work by, a former student, Lei Hu, who did this. So basically, the idea is that given one single spectrum, with limited amount of data, how can we extrapolate in the time dimension? How far back we can go, how far forward we can go to predict what's going to happen to this supernova. Basically, we observe, supernova at this day. Do we know what's going on in the other days? This is just the, in a nutshell, this is what this program trying to do. And, actually now we're also working on a way, actually for the supernova, we can also extrapolate in the time dimension and going to all the other. Okay, if we have one piece of wavelengths, this is a 2D manifold, and said, if you cut in a at a given time, in the horizontal direction, you can predict the vertical, and you can also try to use the vertical to predict the horizontal. Okay, this sounds like whatever that TV show many years ago. Okay, you get both the horizontal and the vertical. Well, so these are the AI, what an illustration called AI may work. And I show you more examples of this, but my goal here is just to illustrate how, what it can do. I'm going to skip these details. And you can always also do, what you can do, you can try to predict with one spectrum or two spectra, multiple spectra, and you can always check and with new observations. So this thing we trained turned out to be very successful because this was done by in the real time. Once you have network in astronomy, you don't need to worry about your model being ridiculous, because it will be thrown away immediately. If you do something wrong, then somebody doing the observations or doing something can check your results because the sky is open. Okay. If you're proven to be wrong, then you need to go back and rework on your model. So this is actually a real-time verification of how this may work. So this supernova is discovered and then observed. Then we put those spectra into the predictor, AI predictor, and then we gave a sequence of spectra, and the later observations actually verified. The observations taken at a later time actually shows, well, perfect match to the predictions. And these are the two examples. You can see, we predict with this, this red line, and then the green line. The black lines are the predictions. The green lines are observations taken at future, times. And here is the same, for this supernova. So this shows that AI can be very useful. Can be actually, with this kind of tools, you can say, it will affect how you make observations. You are going to schedule how you're going to schedule what kind of data you want to take. And the other thing is, as I said, there are two aspects of this. One is the data, the other is the complicated nature of the theoretical models. So how can you turn your theory back to match that, to fit to the data? Okay, you can say in that very high dimension, if you want to really develop a model to match the observations. How can you just imagine you want to sample that space, try to match the observations? It's almost impossible. So for years, astronomers have just developed the models, and then they do their best to run certain code, to run certain theories, and then just draw the theory and the observations together. But it has never been very good. There are huge misses usually, because you can the kinematics can miss, the structure density structures may miss, the chemical structures may miss. So you just to hit the target is really tricky. But AI will be able to help us with that, because you will be able to build surrogate models that accelerate models, so that you can somehow iteratively rebuild your model grid, and you can run certain number of models, and the AI can try to learn to simplify and rebuild the models at a much faster speed. So this is just an illustration of how the supernova explode. In the beginning, this is a carbon oxygen white dwarf, and a nuclear burning started at the center. So that's a thermonuclear explosion just beginning to happen. And then the whole star start expanding because it's heated by the explosion, by the energy injected at the site of explosion, becomes bigger and bigger, and new elements are being produced, nuclear elements being produced, and instabilities develop. So how do you know what's going on there? So this is then, it's like you have a really messy situation, but there are threads. You are using your physical rules try to sort things out. Okay, so we cannot afford to do everything in 3-dimensional, so we assume it is spherical. Okay, the supernova just to begin with in this particular work. Eventually, to get to 3D is another huge amount of work. And once we assume it's 1D, the chemical structures are simplified. They are onion skin-like, but in reality, they never are onion skin-like. Okay. And now this is the chemical distribution. Like you have different chemical elements and the function of the velocity, the onion skin-like thing. And so this is what traditionally people would do. People will eventually converge. After many trials for many years, people, some astronomers are smart. They are able to guess what would be the chemical composition, and they would then be able to, do a pretty good job. Here is the theory compared with observations. The black lines are the theory, and the blue lines are the observations. And you can see, they're not perfect match, but they are somewhat, they are pretty close. But you can see, to really improve this becomes extremely difficult, because this is close to some sweet spot, but really to get it right, now everything is entangled. It's not like, okay, I want to fix this feature, okay, and then I adjust something related to this. Okay, yes, you can do that, but that will offset, affect the fit in other regions. Okay, it's just, you fix this part, the other part will just miss. And our approach with AI actually did a pretty good job. This is Lisa's work. And you can see, this is our fit, and we are able to derive all these chemical structures here, and the density structures in a rather, and, get this kind of improved fits. And this is what I mean by the features are entangled. For instance, you change the iron abundance in a certain layer, like this thing is expanding, you change the color, something one layer of the onion skin, and the whole spectrum will change. It's not just that thing about that single onion skin. And usually we have millions of lines involved in this sort of calculations. Okay, you can see the large number of data involved in theoretical modeling is also mind-boggling. Okay, so then we were able to derive these density structures and those things. And this tool, why are we doing this? Because these are basically this kind of supernova are fundamental to our understanding of the whole universe. Basically everything in this room, including everybody, is probably processed in a supernova like this, like what we did. All the chemical, all this iron in your blood came from supernova. And supernova type 1a supernova is actually applied in cosmology to derive the distance to faraway galaxies that which actually was awarded the Nobel Prize and some many years ago. Okay, and I skip that. And we are actually trying to turn this AI-based stuff into something useful for cosmology, which is basically to use all these features that we can derive from AI to then try to make them to quantitatively evaluate how the property of the supernova, including its brightness, so that we can derive the distances very more accurately, and that's being still being worked on. Okay, so in summary, I think the AI is a new beginning actually for astronomy. It's going to really change what we do, how we do astronomy. And the next decade, there will be not the next decade, just in a couple of years, there will be a huge amount of data that's going to be coming through the newly built wide field survey telescopes. And many universities, many groups, are preparing for this new, writing codes, preparing for the operation of these telescopes. We are going to find, and AI, basically is going to be crucial in all this. So with that amount of data, actually, going to be useless without AI. That's what I think. You need without AI, the more, or that large amount of data will be, it's just no longer the time that you can look at a single exposure and tell and learn a lot. You have to really lump everything together to learn. Okay, here is the sample, well, the summary. So I'm not going to read this, but if you have questions, please. Uh, the wavelengths, well, the spectrum here is actually you're asking how this is the algorithm. Or so basically what we do, we have a training set of supernova, which are observed at different time and with different wavelength coverage. They don't really always cover the wavelengths we want to have. And but we have a training set that with good enough coverage that we pick this through tens of thousands of spectra. We then train the neural network that, well, of course, those data, data needed to be pre-processed. But in the end, we train a neural network that is basically, let's say, a basically a function that with the input being some of the let's say one of the spectra in a training set, and the output will be a sequence of the spectra, so from one to many. Okay, this is basically training that kind of neural network, and which is this why we use LSTM. It's also because this is time sequence. Basically, it's sort of like language kind of prediction. You can draw some analog into that. So that's the architecture we adopted. But today, I think we should be probably using transformer to do this kind of work. It's going to be more, well, it probably will do even better. Yeah. That's exactly correct. So I said these are very complicated physical situations. It's like a million dimensions, which we cannot comprehend with our brain, okay? But then the AI is employed to reduce that dimension. So basically, hopefully, eventually, the ideal case, we will be able to reduce that to one dimension. Okay, then we can understand one dimension for sure. That's going to be the spherical case. So basically, but we are not even well. We basically start with the the problem with a very high dimension. We reduce that into something simpler. But in this case, the geometry, we start with something simple, okay, because we cannot handle that high dimension. But that huge dimension can indeed be calculated. At least break up into three-dimensional something. Uh, you calculate maybe not a million models, maybe a few hundred models, and then you learn to build some surrogate models or something, and probably we will be able to learn the three-dimensional structure. But ultimately, we want to reduce this to something simpler. Okay, so you mean the outliers? There are different ways of being an outlier. An outlier, for instance, in this sequence, have you ever encountered an outlier at a certain epoch? So that actually, this group of objects behaves so well. Actually, we never get that kind of outlier. But you ask another. This is well, actually, I'm not exactly. Well, I take what I said back, because we do have some. Yeah, actually, there are indeed, when we have this, there will be predictions on the other dates that are off from the observations. That don't agree with the observations. So those are actually new discoveries. That means that supernova was not in the original training, not represented well in our training sample. That represent a new discovery. So we actually made the discovery based on the matching, well, by comparing the prediction and the real observations. And that's just some kind of very weird supernova. But it's actually the other way of understanding outlier is that well, it's actually exactly the same. Probably is that the the outlier we call it outlier because it was never in our library, in our training set. So maybe these two are the same. Yeah. What? Yeah, outlier is the discovery. So yeah. And the universe, the same with the transient. It's just uh, sometimes maybe it's not a completely new discovery, like maybe just we viewed it through a certain direction, which then is related to the spherical car or not. It could be, in certain directions, it will look very different. certain or just determine. Well, it depends on how the geometry is aligned with our line of sight. Since we have such limited, well, our sample is a few thousand is still very small. Okay, uh, we we can this 4 pi sky is we need millions to cover everything. Yeah. So yes, so that is really a very good question because in astronomy, I draw this thing as if this there are like enough data. Okay, we never had enough data. Okay, each of these supernovae that we observe. So well, actually, up to today, we have maybe less than 1,000 very well observed supernova that we can do this kind of study. You can see. And this always involves the very expensive operations at telescopes. Each night or each spectra costs you like tens of thousands of dollars, to actually to acquire. If it is from the Hubble Space Telescope, it could just be much more expensive. So, yeah, so these data are indeed valuable, but for the moment, yeah, they are far from what we want. Okay. But that's also shows it's a playground for AI, for these smart algorithms to to get to play their roles. That's a different kind of error or outlier. That's just an error not by nature, but by some kind of observational artifacts. Okay. Indeed, we do have those kind of things. Like we have cosmic ray hates. Yeah, cosmic ray can produce features, and we may have defects in the detector, things like that. We may have cloud. Sometimes cloud come over, affect things, and the atmosphere may produce features on our spectra. So this sort of thing. But in astronomy, the thing is that we don't, you know, if something happens, it will not happen only once. So we have abundance of those. So that's actually another area that AI plays a role, is to reject those features due to this, atmosphere or the cosmic rays or whatever. Yeah.
Okay, and next talk is by Dr. Siegel. He's an assistant professor in mathematics department at Texas A&M University. His research interests are in the fields of approximation theory, mathematical theory of neural networks, statistics, numerical methods for solving PDEs. And today, he's going to talk about symmetry preserving neural networks.
Thank you very much. I want to, of course, begin by thanking all the organizers for putting together this event and thank all of you for your attention. So today I'm going to talk about symmetry preserving neural networks and take different techniques for building these, and then some of the recent work that we've done on this problem. Okay. All right, so just to begin with an introduction here, as we all know, recently deep learning and machine learning have become very prominently used for scientific problems, right? I mean, this is a workshop on scientific machine learning, so there's been a lot of application of neural networks to scientific problems. Maybe one of the most famous examples is this AlphaFold neural network that was used to solve, in some sense, the protein folding problem. But there are also a lot of other, neural network-based approaches for modeling quantum systems, predicting materials properties, et cetera, right? And one of the ways of approaching these problems, right, is you, for example, suppose you wanted to predict some property of a material, right? This is what this schematic here shows, right? So you've got some material and you'd like to predict its properties, right? And you want to train a neural network to do this based upon a large database of materials and properties that you've determined experimentally or via some other method. And so typically the way this would be done, right, is you need to input this material, right, which may be a molecule or a crystal into your neural network. And the way this is often done is via just the positions and types of the atoms, right? So you basically input to your neural network a list of spatial positions and atomic types, right? So you say like at this point in space, I've got this atom, this point in space, I've got this atom, etc. And this is the input to the neural network. And then based upon that, it's supposed to predict some property of the material, right? So this is kind of the picture I want to have in mind, the type of neural network application to science that I want to look at during this talk. And the point is that, when you input your molecule or your crystal structure in this way via, a list of positions of atoms, there are a lot of symmetries to the problem, right? Namely, the physical laws are going to be invariant under translations, rotations, perhaps reflections, permutation of identical particles, right? So the order in which you pass the different atomic positions, it doesn't matter if they're all the same atom, right? And there may be other groups of transformations, right? So the point is that there's often some symmetry group, some group of symmetries under which your problem is invariant if you formulate it in this way in terms of predicting things based on atomic positions, right? And which group you have may depend on your problem. For example, in chemistry, maybe you have rotation invariance, but not reflection invariance for certain types of problems. And in physics, this could happen as well, right? But the point is that in a lot of these problems, you have some physical symmetries that we know the ground truth has to satisfy, right? So we know the prediction function here has to be invariant under translating the locations of all the atoms, right? It has to be invariant under rotating the locations of all the atoms, or giving the locations in a different order. If the particles are the same, it has to be invariant under that. In addition, we typically also have a situation where the ground truth is continuous. So small perturbations in the input are not going to produce large changes to the prediction, right? Like the formation energy of your molecule or your crystal are not going to change dramatically, if you perturb the positions of the atoms slightly. This is typically what happens. So in order to take advantage of this knowledge, right, we know the function we're trying to learn, we know the predictions that we're trying to make satisfy these symmetries. We would like to take advantage of this knowledge by building these into the neural network in some way. And also, we would also like to take advantage of the fact that we know the neural network function is continuous. Okay, so the field of what's called geometric deep learning is concerned with this problem. How do we design neural network architectures that are invariant to certain symmetries and and also preserve continuity? That's also often an important question. Okay, so let me begin by looking at a specific situation here and describing mathematically what we're going to talk about. So I'm going to view my neural network as acting on point clouds, right? So you can view this, for example, as the positions of a bunch of identical particles. So here, this x1 through xn, these are positions in RD, and you've got n of them. So you can think of it as the input here represents n particles in RD, right? So D typically would be like 2 or 3, right? And you've got n could be quite large, right? So you've got n atoms in R3, and this is just a list of the positions of these atoms. Okay, so the different symmetries I want to look at, one of them is rotations or rotations and reflections. So this SOD, this group SOD means just rotations, O of D, orthogonal transformations, which includes rotations and reflections. And the way this acts on my point cloud is just by simultaneously rotating all of the positions, right? So you can think of it as this is a set of points in RD, right? And I just rotate the whole entire thing, right? So often this, your physical laws will often be invariant under this, or the function you're trying to learn will not change if you rotate all of the points, right? The other action I'd like to look at is permutation. And so this is the situation where all of these are identical particles, right? So these are all the positions of a bunch of atoms, and it's all the same atom. And so this means, of course, that the order in which I give you these positions should not change the prediction of the neural network, right? Because it's the same same configuration regardless of the order in which I give you these points. And so the way we write this is you have the action of the symmetric group or permutations on this point cloud, which is just given by permuting the different columns, right? Permuting, you know, if I change the order of the points, then that is the action of sigma here. You can also consider, for example, the combined action. If you have a cloud of points consisting of identical particles, and then you want it to be, you want your prediction to be invariant. It first of all doesn't depend on the order in which you give the points, and also doesn't depend upon how you rotated them, essentially. Okay. So let me formulate precisely what we want here in a mathematical way. So we call a function, so given a group G acting on two sets, X and Y, so here X is basically our input point cloud, and G is either rotations and reflections, right, or permutations. We say that a function is equivariant if it commutes with the action of G. So this is this equation 3. And we're specifically going to be interested in this talk in the case where G acts trivially on Y, so in which case it's invariant, right? So let's, if you understand what this means, that's great, but if not, just focus on this equation 4 here. Basically what we're saying is we want our prediction function to be the same regardless of how we rotate the input or permute the input. So if we transform the input X, we don't want the prediction to change, right? That's what we design, right? That's what it means to build these symmetries into your neural network, is that it satisfies this equation. It is, the network function is invariant under rotating or permuting the input. But one can also, of course, consider more general groups G here. All right, so the goal of the problem that we want to consider is how can we construct neural network architectures which are G invariant and also universal, in the sense that any continuous G invariant function can be approximated to arbitrary accuracy by this network architecture. All right, so let me begin by talking at kind of a high level about different ways of doing this. So this is actually quite a big field. Here's a bunch of references. That's not complete by any means, but there are at a high level kind of two ways that you can build symmetries into your neural network. The first is methods that are based on transforming the input in some way and averaging. So these are methods that can be built on any kind of base neural network architecture, and you essentially average the inputs or transform the inputs in a certain way. We'll see exactly what I mean by that later. To make the network, to make a non-invariant network, non-invariant base network, to make it invariant. Okay, and these are called canonicalization or weighted frames, for example. On the other hand, another thing you could do is you could try to design a neural network architecture that by construction only parameterizes invariant functions. And this has been actually very successful for permutations. I'll talk about deep sets later in the talk. This was an early permutation invariant architecture that was very prominent, and transformers actually, if you remove this positional encoding, are also permutation invariant. So these are kind of at a high level two different ways of the two main different ways of obtaining invariant neural networks. You either start with a general architecture and you make it invariant via some pre-processing of the inputs, or you design an architecture which is by construction already invariant. Okay, and I'll talk about both of these approaches, but I'll start with the first one. Okay, and I'll talk specifically about weighted frames, which is some work we've done on this recently. So let me be a little bit more specific about what I mean by methods based on transforming the input and averaging by giving some examples. So one of the, perhaps the simplest example of this is something called group averaging. So what I do here is I take some non-invariant neural network architecture, this F theta right here. Theta are the parameters, F is just some regular feed-forward neural network. And what I do is that function is not going to be invariant for most values of the parameters theta, right? But what I do is I make it invariant by saying, well, instead of taking F theta of X, I'm going to take F theta of G times X and then average over the group G. So basically, for example, in the case of point clouds and rotations, what you're basically doing is you're saying, well, I'm going to apply my network to all possible rotations of my input and then average that. So it's easy to see by construction that this is going to be invariant. And in addition, if f theta is already invariant, then you just get f back, right? So if the function you're applying this averaging to is already invariant, then the average will just be the same as that original function. So it's a projection onto the set of invariant functions. And from this, we can deduce that if f theta is universal, then this averaged f theta is going to be universal for invariant functions. So if with my base neural network architecture, I can approximate any continuous function to arbitrary accuracy, then the averaged f theta can approximate any continuous invariant function to arbitrary accuracy. And in addition, if f is continuous, this also preserves the continuity of f. So this operation, this averaging operation, if you average over the whole group, preserves continuity and even all higher order smoothness of the function f theta. However, the major disadvantage of this is that this is really inefficient, right? You're averaging over the entire group G. So to implement this exactly, you would need to apply your neural network to all possible, say, rotations of the image of the input G. In that case, there's infinitely many, so it's not possible to do it exactly. But for example, for permutations, you would have to apply your network to all possible permutations of the input point cloud, and average those, which is not something that is computationally feasible. So we'd like something more efficient. And on the other end, on the other extreme here is something called canonicalization. And so here the idea is, well, instead of averaging over the entire group, I'm going to average just over a single element, but it'll depend on the input. So basically, in words, the way to say this is you take your input and you transform it into a canonical position before applying the neural network. So if you think about this in terms of, point clouds and rotations, right, you're saying, given any input point cloud, I'm going to rotate it to some standardized position before passing it to my network, right? And that's, in this way, I can take a non-invariant network and make it invariant, right? And make this function invariant by simply rotating or transforming to a standardized position, right? So the properties we need of this canonicalization function is that, well, it maps things to the same orbit, right? So you don't, you actually just rotate the input, you don't change it in any other way. And it's also invariant. So all of the rotations of X get rotated, doesn't matter how X was rotated when it was input, it always gets rotated to the same standardized position by C. So this is called a canonicalization. And again, you can verify that it's a projection onto invariant functions. And so if f theta is universal, then so will this canonicalized function. This canonicalized function will also be universal. Okay, but there's, so in order to give a little bit more intuition here, let me give some examples of canonicalizations in the specific situations we were looking at here. So again, if we consider point clouds, if we look at the symmetric group acting on point clouds, one example of a canonicalization would be I could sort the input lexicographically, right? So I could take the x coordinates and sort my points by the x coordinates, right? So again, the idea here is you're inputting the positions of a bunch of points, and you want things to be invariant to permutations. So you want it to not matter what order the points are presented to you. So in order to achieve that, you can say, well, no matter what points you give me, I'm going to order them in some standardized way. So for example, I'll sort them lexicographically, sort them by x coordinate, and then if there are ties, sort them by y coordinate, etc. Another example is if you have, for example, rotations acting on point clouds in 2D, what you could do is you could say, well, however you input your point cloud, I'm going to always rotate it so that, say, the first non-zero column is on the x-axis, or the longest vector is on the x-axis. So essentially, these are just rules telling you whatever your input is, this is a rule that tells you how to transform it to a standardized position. And that's what a canonicalization is. And if you do that before passing it through your network, you build the invariance into the neural network, even if the original architecture is not invariant. Okay, So this has been well studied. There's a lot of methods people have proposed to construct canonicalizations, including even using neural networks to learn them. But one major question is, well, if I do this, can I preserve continuity? So it may be that by canonicalizing your neural network, you make the canonicalized function not continuous anymore, right? So maybe even though the neural network architecture represents continuous functions, that by canonicalizing you break continuity, and that would be not so great because in most situations we want our prediction function to be continuous, right? Okay, so let me also talk about this generalization of canonicalization and the group averaging, which is called frame averaging. This was introduced recently. I mean, basically, you can think of it as something in between the two, right? Instead of averaging over the whole group or averaging over a single element, we average over some subset in order to achieve the same thing. So I'll go a little bit quickly through this. This is basically what you're doing here is given an input, you map it to some set of canonical, some set of sort of canonical elements G, and then average over that. So, canonicalization is averaging over one element. Group averaging is averaging over the whole group. If you average over something in between, dependent on your input, this is called frame averaging, and has been introduced recently as a generalization of these. Okay, so really the question is, can these methods preserve continuity, right? So can canonicalization preserve continuity? And I'll start with a very simple, it's a very simple proposition, which is that if your canonicalization preserves continuity, then that happens exactly when the canonicalization map C is a continuous function, right? So meaning that a continuous neural network gets turned into a continuous, if you start with a continuous neural network and you canonicalize, you'll end up with a continuous function if and only if the canonicalization map itself is continuous, okay? However, it turns out many of the canonicalizations people proposed are not continuous. For example, the two that I showed before, lexicographic sorting is not a continuous operation, right? In 1D, if you just sort a one-dimensional vector, right? So if you just have n numbers and you sort them, this is continuous. This is a continuous way to canonicalize. But if you have two, point clouds in 2D, if you have a bunch of 2D vectors and you sort lexicographically, it's not hard to see this is not continuous. And similarly, if you look at, for example, point clouds in 2D with the action of rotation, then you can also see that, for example, rotating the longest vector to the x-axis is not going to be continuous because small changes in your input can change which vector is longest, basically. So, it may be that perhaps we just didn't choose very good canonicalizations here. Maybe there is some way of standardizing the input that is continuous, but it turns out, and this is one of our results, it turns out that you often can't do this. So is there even a way of canonicalizing continuously in these situations that we've looked at? So here's what we've been able to show. It turns out that if you have the action of permutations on point clouds, then if you're in D equals 1, right, you could just sort it, right? If you just had a list of n numbers, sorting it is continuous, and that, of course, canonicalizes, right? But if D is bigger than 1, then there's no way to continuously canonicalize point clouds for the action of rotation. And similarly, in the case of rotations and orthogonal transformations, there is only a continuous canonicalization if the number of points is less than the dimension or less than or equal to the dimension. So with a lot of points in low dimensions, there's no way to continuously canonicalize. So if we want to preserve continuity, we need to do something different, something more general. And you can ask, well, okay, what about this frame averaging that we had before? What if I average over instead of a single element, right, like canonicalization? Suppose I average over some set of rotations. In this case, you still can't preserve continuity. For example, in the case of permutations or rotations, and the issue here is basically that you're averaging with equal weights. Okay, you're averaging with equal weights, and So what we did next is to introduce a generalization of this, which is basically instead of averaging with equal weights, suppose you can take a weighted average, right? So what's happening here is you have some input x, right, some point cloud, and depending upon your input, you take some weighted average of the rotations or permutations of x, and you average the value of your network over this, right? So by going to weighted averages, that's what we looked at, right? So again, group averaging, you average over the whole group, right? Canonicalization, you have a single element. But now what we're doing is saying for each input, I'm going to take a weighted average over different transformations of x. And maybe in this way, I can preserve continuity more efficiently, if that makes sense. All right. So we would also like this method to be as efficient as possible. So we say the size of this frame is the maximum number of elements that I have to average over. So the maximal size and support of this distribution f of x of this. Yeah. So we're taking a weighted average of elements. What's the largest number of elements you need in this average? Okay. So first question is, well, does this improve things, right? We saw that with canonicalization or with unweighted frame averaging, we could not preserve continuity without basically averaging over the whole group. Can we do something better if we allow weighted averaging? And it turns out that we can. We can show that if you look at the action of permutations on point clouds, then there is a weighted frame. So there is a way of averaging over different permutations with certain weights, which preserves continuity of the input of the base neural network, and where you will always only need to average over, well, n to the 2 times d minus 1 points. If you have point clouds with endpoints in RD, it's still quite a large number of things that you need to average over, but a lot less than n factorial, which is the size of the group. And similarly, we can construct weighted frames with also polynomial size for SOD and OD, which preserve continuity. In this case, the size is like n to the d minus 1. I will remark, though, that we don't know if these are the best possible. So perhaps there's something better you could do here. Perhaps there are smaller weighted frames that also preserve continuity in these cases. And they're still very large, so we implement these empirically when we actually do things. All right, so let me kind of give some experiments to illustrate the point of what I'm talking about. Basically, why do you want to preserve the symmetry, and how these methods actually work in practice. This is a very simple example. We're going to start here with the MNIST data set, but we're going to make the problem more difficult for our neural network. So instead of giving as input the pixel values, right, and predicting the digit, what we're going to do is we take each of these digits and we process it into a point cloud. We essentially randomly sample from this, from this digit. So you can imagine, you can imagine the ink on this digit is giving you some distribution. You kind of randomly sample points from it. So we process each of these digits into point cloud data, and so what the neural network sees is the list of a bunch of 2D coordinates in a random order, where the digit has ink, essentially. And based upon that, we would like the neural network to classify the digits. Of course, this is by construction permutation invariant, right? Where, because this processing this digit into a point cloud, it should be classified the same no matter what order these 2D coordinates are presented, right? Okay. And then what we did is we basically just started with a general simple feed-forward network with 3 hidden layers, right? And we tested group averaging, weighted frames, and these discontinuous canonicalizations, and saw what happened. So if you don't impose the permutation invariance, it performs quite poorly, right? You get just 25%. This is due to the fact that, you really need to put this symmetry into your network in order for this classification to work, right? The group is huge. Permuting 100 points is a huge group, and so not building this invariance makes it very difficult for your method to generalize. So if you build the invariance in via discontinuous canonicalization, so here we took lexicographic sorting, you do much better already. You just by building in the permutation variance, you get to like 85%. And now if you, however, if you use our weighted frames, right? So if you use this technique, and I didn't describe exactly what the frame is, but if you use this technique of averaging, taking a weighted average over different permutations in the right way, it turns out you can significantly improve the accuracy, although you need to empirically average over a lot of samples, right? So here, the size of these weighted frames is still way too large for us to implement it exactly. So we sample from them empirically. And if you take enough samples, you can significantly improve the generalization of this method simply by also enforcing continuity, right? So the point here is, here you've got invariance but no continuity, and here you've got invariance and continuity, and it makes a difference, right? The method generalizes better if you also enforce continuity. And just finally, to compare this with, this is group averaging. If you average over the whole group, it essentially does nothing because the group has size 100 factorial, right? You can't, we can't do it exactly. So even if you do it empirically, it's the same basically as not enforcing any invariance. So you're never even going to see the same permutation twice. Okay, so the point of this is that, in this very simple toy problem, it helps significantly to enforce both continuity and the permutation invariance. And so for realistic problems that scientists, engineers are working on, we expect it will also make a significantly better to enforce both the symmetries and the continuity. And we have techniques for doing this, although they may be a bit more expensive than canonicalization, for example, right? So, yeah. But we're still actively working on this. We don't know what the best possible way of doing this is yet, so we're still working on developing more efficient methods that can enforce both continuity and invariance. Okay, so finally, that's kind of the first part of my talk. Now I want to go to a different subject. So what I've talked about so far has been methods of designing invariant neural networks by taking a base architecture and doing this kind of averaging or canonicalization on top of it. Now what I want to talk about are methods for designing invariant neural networks where you build the invariance directly into the architecture of the neural network. So in particular, I want to talk about some analysis we've done of an architecture called deep sets. Okay, so deep sets, this is a neural network architecture which is designed to induce permutation invariance. Okay, so here our input is, again, a point cloud. We're not looking at rotation invariance right now. We're looking just at permutation invariance. And I want the function of the positions of these points to not depend on the order in which I present them to the network. Okay, so basically I want it to be a function of the set of points, not dependent upon the particular order. So the architecture that was designed here, this deep sets architecture here, which was introduced in 2017, is as follows. What I do is I have two neural networks, phi and rho. The first neural network, phi, takes all of these input positions and it encodes them in some much higher dimensional space, Rn, where n is kind of you can think of it as a feature dimension. So I take some embedding map, some neural network phi, which I use to embed the point positions into some much higher dimensional space, Rn. Then I add up all of these embedding vectors and apply another neural network to that maps you then back into R, right? And then, of course, I train both phi and rho together, right? So the parameters of my network are the parameters of both phi and rho. And the idea here, right, is this is by construction permutation invariant, because the same embedding map phi is applied to all of the xi's, then it's all just summed together and you apply another neural network. So the order of the xi's here doesn't matter, right? Because, well, the order in which you take this sum doesn't matter. So it's no matter what the values of the parameters, the function is guaranteed to be permutation invariant. And this is what I mean by an invariant architecture, right? You have to design your architecture specifically to build the invariance into it. Okay, and also notice that this is always going to be continuous if rho and phi are continuous, right? So if you have a continuous activation function in phi and rho, this is going to parameterize continuous permutation invariant functions. But, a key question here is, well, so this is great if it works, but is this a good architecture, right? Is there some way that we can understand whether this is a good architecture or not, or maybe by constraining the form of our function f to take maybe by constraining our function f to take this form in equation 12, maybe we're making it a lot more difficult. Maybe we're constraining its expressive power, right? Maybe we're making it more difficult for it to represent permutation invariant functions. So there's two questions that I want to essentially look at here. The first, most basic one is universality. Can you actually approximate any continuous permutation invariant function in this matter, right, with this particular architecture? And then to go beyond that, you can ask about approximation rates. Well, how efficient is this architecture going to be? And especially, how efficient is it going to be in terms of the number of parameters compared to just a standard, an unconstrained feed-forward neural network, right? If I don't build the permutation invariance into the architecture like this. Okay, so first, let's look at universality, and this was actually addressed in the original paper as well. At least in the case d equals 1, and it was then generalized the case d greater than 1 in a follow-up paper. But the way that this works is via polynomials. So the way that this proof works is via polynomials. You basically show if I take any permutation invariant polynomial, I can always factor it in this form 13, and then by approximating phi and rho, which are now polynomials by neural networks, I can get universal approximation. The issue with this approach, and this does prove universality, so any continuous permutation invariant function can be approximated to arbitrary accuracy by a deep sets network. But this approach doesn't give you any quantitative rates of approximation. So it doesn't tell you how large the network's phi and rho have to be to get a certain accuracy. All right. And so that's the next question that we then looked at is, well, can we get some approximation rates here? And especially, how do these compare with non-invariant architectures? So is it the case that by constraining, by considering the deep sets architecture, do you dramatically increase the number of parameters you need to approximate certain functions, right? Compared to just a regular feed-forward network. That's basically the question we want to ask. If that's the case, then maybe it's not so good to use deep sets, right? But if not, maybe deep sets is a pretty good thing to do, and in practice it does work quite well. Okay, but in order to formulate this question precisely, you need to make some assumptions on the target function f, right? You cannot talk about rates of approximation with no assumptions on f. So the assumption that I want to make is basically this very simple assumption: f is what's called Lipschitz, meaning its gradient is bounded by 1. So I assume that f has gradient bounded by 1, and I want to know how efficiently can deep sets approximate it, how efficiently can a regular neural network approximate it. Okay, and just to kind of give the results here, what we were able to show is the following. Don't worry about the technical details of this theorem here. Let me just unpack what it means here. But the point is, suppose you have some permutation invariant function with bounded derivatives, right? So some Lipschitz permutation invariant function, and you'd like to approximate it to a certain accuracy epsilon. Then you can do this with a deep sets network whose parameters scales like epsilon to the minus d times n over 2, where d is the dimension, right? And n is the number of points. And the inner feature dimension has to grow like epsilon to the minus d. So the inner feature dimension has to get bigger as you want to get a higher accuracy. We don't actually know what happens if you fix the feature dimension and only allow the size of the networks to grow. But okay, so this is what we are able to obtain. And how does this compare with the general feed-forward neural network? So it turns out that for a general feed-forward neural network, if you have a Lipschitz function in dimension d, and you want to approximate it to accuracy epsilon, then the number of parameters you need is something like epsilon to the minus dimension over 2 to get accuracy epsilon. And this is sharp. So if we compare this with the previous result for deep sets, right, where if you have n points in RD, the problem dimension is n times d, right, because that's the total number of parameters required to specify the input. Then a Lipschitz permutation invariant function can be approximated by deep sets with this epsilon to the minus d over 2 times the log factor, parameters, and using a general MLP, it's epsilon to the minus d over 2. So basically, there's no difference really asymptotically between deep sets and a regular standard neural network. So you can kind of say this as there's sort of no loss of expressivity in using this invariant architecture. So this invariant architecture is just as efficient at approximating permutation invariant functions as a regular feed-forward neural network is at approximating a general function. However, in our construction, we do require the feature dimension n to be large. This kind of indicates if you're going to use this architecture in practice, you should increase the feature dimension. You should use a large number of hidden features. All right, yeah. So let me just conclude here, right? So what I've tried to kind of show is different methods that you can use to make a neural network architecture, make a neural network function invariant to symmetries while also preserving continuity. Those are kind of the two things which we think are important for improving their generalization capabilities. And we looked at a bunch of different ways of doing this. Well, two high-level ways. On the one hand, you can start with a general architecture and then use some sort of averaging operation to make it invariant and preserve continuity. And on the other hand, you can design a neural network architecture which is invariant by construction. And I've given some way of analyzing basically both of these approaches, but there are many open questions that perhaps some graduate students here, would like to look at, which is, for example, for these weighted frames, we don't know what the smallest possible ones are. We're still looking into that. Also, we'd like to develop approximation theory for other invariant architectures. We've so far only done this for this deep sets architecture, but there are other invariant architectures like transformers for permutations, or there are also invariant architectures for rotations that we haven't looked at yet. And for people applying neural networks in scientific problems, the message is you should build your symmetries into the network and also preserve continuity, and we can help you do that. We know this is basically what we're studying, so perhaps we can help you do that in practice. Yeah, so with that, I'll conclude and thank you all for your attention. I'm happy to take any questions. Well, yeah, so I don't have a real life example. The only thing I have is this kind of toy example. This toy sort of MNIST classification from point cloud sample. Right, so I mean, I'm not really a practitioner. Like, I don't apply deep neural networks to practical problems. But this toy example, we constructed it to try to illustrate that it's important to preserve symmetry and continuity, basically. And so for this particular problem, we observed that the generalization has improved significantly. And so what's improved really a lot if you enforce the permutation invariance, right, the symmetry. And it's also improved even more if you're able to also preserve the continuity, if that makes sense. So we'd be happy to work with someone who's solving a practical problem to build these methods on top of what they do and see how it improves things. But yeah, I don't have a really practical example, just this kind of toy example to illustrate the point of you should preserve symmetries and continuity if you can. And we have ways of doing it, but there's still a lot of open questions. Yeah.
Yeah. So thanks.
Right. Well, yeah. So it's the function that the neural network represents, right? So this, for example, in this, if you look at, averaging or canonicalization of this f theta, that is the neural network function, right? Theta are your parameters, right? Your neural network takes some input, gives you some output, right? So that is a function itself, right? And so now what I'm saying is, instead of taking that function, for a given input, I take all possible rotations of that input, run them all through the network, and then take the average of the output of my network over all of those, if that makes sense. Or for canonicalization, right, I take my input, I rotate it to a standardized position, and then I pass it through my network. So that changes the original function, right? I'm not just passing the input through the neural network, but I'm doing something, I'm pre-processing the input before passing it through the network, if that makes sense.
Yeah, so when you say like the function of weights and biases,
It's a function depending on the weights and biases,
yes,
right? So it's a function of the input that depends on the weights and biases, yes, right? Right, right. So I mean, the issue is that here the problem is permutation invariant, right? Because the input to my network is a list of 2D coordinates, right? A list of points in 2D that, like for example, for this for this zero, right? It's like a bunch of points that are like 100 points that are kind of like in the shape of a zero, right? Um, so we took each of the handwritten digits and processed it to this cloud of points, right? And then we present the neural network just the 2D coordinates of these points, but in some random order, right? So in the training and test data set, we present the coordinates here in a random order. And as a result, there's there's so many different possible permutations that you're seeing the training data set permuted in all kinds of different ways and the test data set permuted in all kinds of different ways, but they never like overlap. There's not gonna, if that makes sense.
So
like
you say you're doing permutations while passing in the input data. You're saying, well, for simplicity, I'm saying, okay, there's a yellow region and a black region. They have different values.
Right.
But the coordinate and the values same. You're just changing the order in which it's being passed, right?
Yes, I'm not even passing any values. I'm just passing coordinates, which are coordinates of a sampling of the points where it's yellow, right? So I'm just passing a list of coordinates in a random order to the network, but of course the digit that you get, it should not depend on the order. By definition, it doesn't depend on the order in which you get these points. So that's what I mean by permutation invariance. But if you push all these coordinates through a neural network, it doesn't know anything about permutation invariance, right? And since the amount of data you have is only like in MNIST 60,000 training images, and the number of permutations is 100 factorial, you're not like seeing enough permutations for the network to learn the permutation invariance, if that makes sense. Yeah, and so that's why you generalize so poorly, right? And there's a huge jump if you just get the permutation invariance, you already are doing much better, right? If you just standardize, if you, instead of giving it the points in a random order, you give it the points in sorted by x-axis, then you already do much better, if that makes sense.
And this permutation invariance is more from an architecture point of view. If I'm thinking about loss, we don't generally talk about permutation invariance, right? The motivation.
Right. Yes, I mean we're not building this into by adding a term to the loss function or something. We're trying to do it either by designing the neural network architecture to always be permutation invariant, or by pre-processing the input in a way to make it permutation invariant, if that makes sense. Yeah. Right. So good question. I mean, actually, the way that we end up doing it is we sample, right? So we don't do this frame exactly because it's too big, even in this case, right? D is 2 and N is 100, so the frame size, like 10,000. So we don't run things through the network 10,000 times, right? Instead, what we do is we sample from the frame, right? So we instead of actually doing the exact weighted average, we sample the different rotations with those weights and then empirically average. It turns out that's actually the easiest way to describe what these frames are in the case of permutations and rotations. But yeah, so when we do that, and when we train, we take only one sample actually, and then when we test, we take up to 25. So what it does is it increases the inference time. So it's sort of, you can think of it, if you are familiar with data augmentation, you can think of it as kind of a more efficient version of data augmentation. But yeah, at inference time, so when we actually apply the model, it does increase the cost by, in this case, factor of 25, right? So it does make things more expensive, but that's the cost of preserving continuity in addition to the invariance. So yeah, depending upon your application, and depending upon your application, you may need to average more or less. So there's a trade-off there as well. You can see if you average. So this is just taking one you actually do worse. If you average with 5, you get it roughly the same, and then you start with 10, you get this. With 25, you get this, right? So there's sort of a trade-off. The more averaging you do, the more accurately you implement the weighted frame, the better your generalization slowly gets, because you're enforcing continuity better, if that makes sense. But yeah, so and unfortunately we can't implement the frame exactly; it's too expensive. So we have to do this kind of averaging. What this is, yeah, but the frame is different, right? So for yeah, so it's a yeah. I mean, I can describe what it is exactly, actually, in the case of permutations. So here the canonicalizations we sort along the x-axis, right? It turns out what the weighted frame in this case is you pick a random direction and you sort your vectors in that direction, and then you apply the network. And you can show the number of permutations you get in this way is like n to the 2d minus 1. And so what we do here is, during training, every time we see a training data, what we do is we sort it in a random direction. And then at test time, we sort it in 25 random directions, run those through the network and average it, and you get a better result than if you just averaged over this, if you just sorted along the x-axis all the time. Yeah, I mean, that's, so the thing about, well, so with MNIST, right, I mean, like you said, you could, like, there are different symmetries you could have, right? You could, I mean, the translation symmetry for MNIST is kind of built into the convolutional neural networks, right? That's and you could also have kind of rotation or reflection symmetries, but it's kind of a discrete set of symmetries, right? Because you have to, yeah. So we did not look at that, actually, but yeah, you should. That's actually a good point. You should always be able to add it, right? Because we don't change the architecture, we don't change anything about the neural network. It could even already be trained, right? And then we would just do this averaging on top of it, if that makes sense, right? So I mean, you wouldn't need more ways because you'd have the exact same architecture. The training time would not increase, but the inference time would increase, if that makes sense. Yeah, so it would increase the inference time. And yeah, so also, to get back to your previous question, data augmentation basically corresponds to group averaging, right? So this is exactly data augmentation. And so essentially what we're proposing is like a more efficient form of data augmentation, in a sense that, yeah. Yeah, so but you should, even if you have a network that's already trained that doesn't enforce the invariance, you can build this on top of it. You know, you can do this frame averaging. Then you may need to retrain a little bit. You may need to fine tune it with this averaging on top of it. But it should still, I would expect, improve performance. But it will make the inference more expensive because you have to average when you evaluate the network. That's kind of the biggest drawback. So it's not clear if that would be worth it in a given practical application. That's what we need to figure out. Yeah, yeah. Essentially, yeah. It makes it generalize better, right? Because you need less data, right? Your network already knows, right? It has the symmetries built in, has the continuity built in. It already knows it's looking for a symmetric and continuous function, and it doesn't need to learn that from the data, if that makes sense. So it should reduce the amount of data you need, and thus improve the generalization accuracy. That's the idea. Yeah. Okay, thank you so much.